Okay, so chapter 9, problem 71. Two identical uniform beams are symmetrically set up against each other, as in figure 9-87, on a floor with which they have a coefficient of friction, mu s, is equal to 0.50. What is the minimum angle the beams can make with the floor and still not fall? Right, so we want to find the minimum angle that they won't fall at. As always, with a lot of these questions in chapter 9, we want to use a free body diagram. And here's the diagram right at the bottom there, the bottom left. So of course we have the center of mass is where all the mass is going. Well, the mass is going to act as if it's centralized there at the middle, and so we're going to have mg pointed downwards there. We want to have the force. So here I've only drawn the left beam. So I'm saying draw a free body diagram of one beam because you can really use the forces. And like you can, when you understand the forces, you really don't need to have both of them there. I mean, you can draw both if you like. So feel free. But I'm just going to draw one. So yes, we have the force of the beam at the top, right? Let's just go from the top and downward. From the top of the free body diagram, like northeast to southwest. So the force from the beam, that's just from the right beam hanging up next to it, right? So the right beam is going to push it that way. And Newton's third law, by the way, tells us that if the right beam is pushing on it that way, then there also must be an equal and opposite force on it from the left beam, right? So if the right beam is pushing the left downwards, then the left is going to push the right upwards, right? So that's one thing to note for future. Then I already mentioned the force due to gravity. But then we also have the angle there at the bottom that will be given. Or actually, no, we won't be given the angle. We may find it later. We're searching for the angle. That specific angle, not the one above the line or anything, is just going to be what we're looking for. And then you also have the normal force pointed upwards from the ground, so the ground's pushing the pole up, and then you have the friction force for whenever it starts sliding. If you can imagine the beam falling to the right, and so eventually that bottom piece, the junction where the normal force and the friction meet, is going to move to the left. And as we all know, friction goes opposite of the direction that you move, so that's why it's pointing inwards or to the right. And with all of this, we have to be able to work with these angles. So when it comes to the length of the beam, because we can't just call it L, right? It's not pointed straight up. So it is dependent on the angle, what the length of the beam is, what the X length and the Y length will be. So in terms of Y, you're going to have L sine theta as the length, and then in X, you're going to have L cosine theta as the length. As was stated before in the problem, the coefficient of static friction is 0.50, so we're going to use that later. From this, we can start doing some Newton's second law and see what we can get out of that. So some of the forces in the y direction, you have normal force up, gravity down. That just means that the normal force is counteracting gravity to keep it above ground, so it's equal to mg. If we go to some of the forces in the x direction, now you see that there's only two forces there. You have the force due to friction and the force of the other beam, and so these both are equaling to zero, the sum of the forces, because it's assumed that in that moment that we're looking at it, it's not moving, but it can move, right? So but this would just tell us that the frictional force is equal to the beam force. But we're not really going to focus on that much. It's not so important. The one that's really more important is below it, that generally the frictional force is equal to the coefficient of whatever friction is happening. In this case, it's static because we want it to not be moving. Like we want it to get to that minimum angle where it will stop, and that's really why we're allowed to say it's zero. So since there's no acceleration. But it could easily be kinetic as well. We could have coefficient of kinetic friction, coefficient of restitution. There's a lot of different things that could fit in that spot. But in this case, it's going to be the force due to friction is equal to the coefficient of static friction multiplied by the normal force, which we already know the normal force is just mg. So it's just mg times mu. Very, very simple, right? But the next part is going to require us to take the torque about the top of the beam. So we can't really use we already did, right? I was going to say we can't use the forces here, but we already used the forces, and we basically got all the information that we could out of Newton's second law, at least in the linear terms. But we didn't think about it rotationally because it is going to be falling, and so there's going to be forces acting at a distance, which, if you think about it, cause a torque, right? So if there's an angle between, if you have a force acting at a distance on a lever arm, for example, like a wrench, then there's going to be a torque. And if you have it, it's going to be maximized whenever the angle between them is 90. So we always want to go for those 90 angle torques. But anyway, you want to take the torque about the top of the beam. So this is just a portion of the drawing I drew here. That's the F beam pointing to the left, and then the arrow that I drew is just the direction of positive torque. So we're going to call clockwise positive, and we're going to call counterclockwise negative. That's what I have in the parentheses there. And then the side note, we're going to say that the force due to the beam is strictly horizontal, not only because of symmetric geometry, but that is one reason. Since it's symmetric, they're going to cancel each other out, and the vertical forces, will cancel each other out, and you're going to have to only deal with horizontal. But also, the beam force is strictly horizontal, since Newton's third law tells us that if the right beam pushes up on the left will push down on the right, and so on and so forth. So this is what I mentioned at the beginning. So ignore the crossed out stuff, but I'll read the rest. So we choose force from the beam as the anchor point, since no torque will be created as a result. So to have a torque, you need to have a distance, you need to have a force acting at some distance. So if we choose the point where the beam force is, there can't be, if we choose that as our anchor point where it's going to be rotating about, there can't be any distance. The distance is 0, so we essentially nullify the need for that force at all. So then the next thing we should do, instead of using the linear Newton's second law, this is kind of a fudge term. No, I don't think anyone really says this, but I like to call it that just to help me memorize and understand it. We should use Newton's rotational second law. So we technically consider F equals ma as the linear one, and then this is the rotational one. So you have the sum of the torques is equal to I alpha. And so this is a direct rotational analog to the linear version, F equals ma. I is just the moment of inertia, the mass, and alpha is the angular acceleration, which is rotational acceleration. But it's equal to 0 anyway because we're in equilibrium, right? So very easy. So next we want to have all of our torques, right? And so before you follow through and try to understand everything, let's just go from the top down. So the sum of the torques is going to be, well, we have to look back at our first picture, right? What's going to cause a torque? So if we said that this is let me get a color here. We said this is going to be our anchor point. Right here, there's red. And then you want to have positive torques this way. So let's see. Well, I see immediately that there's a lot of forces working at distances, right? There's 3 forces, as you can see. So you can imagine if there's 3 forces working at distances, then there's going to be 3 terms in the sum of the torque equation, right? Because you're going to have to include them if they cause a torque. So the force due to gravity is going to cause a torque, but it's at an angle, right? So we actually have to use trigonometry for that. I should have another page that explains everything. Actually, yes, I do. So we'll come back to this page, but you can see that we do have those 3 terms, and they all include the forces I was talking about: the normal force, force due to gravity, and the frictional force. But here's one. It's a little bit of a busy picture, but try to bear with me here. So let's just go to maybe like the right side and towards the middle. So if you see that I have one that's called torque mg equals d times f. D is just the distance, force is just the force. You can really call it whatever you want, r, d, s, whatever. It's just, I'll tell you what it means as long as you understand that, it's all that matters. So the distance away, let's just focus on mg for now. and just ignore everything else on the plot. You can cover it out with your hand. Just look at mg and the f beam up to there. So if you look at it, the force due to gravity, since it's centered in the middle, it's halfway. The distance that it is away from the anchor point is just half of L. So we just need to do half L. That's why we have that distance there. Then we want to find the force, right? So we already know the force is mg, but it's at an angle, right? This is not exactly the maximized. This isn't that maximized torque yet. We haven't got sine of 90, because there should be also a sine theta, but whenever you do sine of 90, it's always just 1. So yeah, looking at this, we essentially want the y component because, well, yeah, we want the y component because this is not going to be going, this is going anti-clockwise, right? If you look at mgy, it's going to go the opposite direction of, no, it won't. But in any case, mgy is the one that is perpendicular with the lever arm that goes from the anchor point to the mg. So that's the one that we're interested in. And how do we find what that's? How do we find which trig function to use? If you have that question, then this should answer it. So since we want mgy and we have mg, since we want mgy, but we know only mg, we probably don't know what mgx is, so it's better to just go with adjacent over hypotenuse, and so you end up just getting cosine there. This is where the cosine comes from. Similarly, we can just go right under that to the normal force. It's the same thing. You have to break up the vector into components first, and after you've done that, you can after you've broken the vector into components, then you can, as long as you make sure the angles are good in the right place, then you should be able to find that it's the perpendicular one you want, right? Yeah, and as it's falling, the normal force is going to be positive, right? Let's see if we have that here, right? So as it's, if you can imagine two ends, like I have my fingers on the two ends of the pole here, and if it starts falling, my right finger starts going down and my left starts going up, you can see that the normal force follows the positive direction. The frictional force also follows the positive direction. So I have it drawn, I have that drawn the wrong way, but it should be an up arrow there, not down there. Yeah, the frictional force and the normal force are pointing up, and the weight force is pointing down, and so that's essentially where we get all of our sines. And the same thing for the normal force as the same for the normal force as for the weight force, just in terms of the trigonometric function, because the angles, you just deal with, you want the adjacent over the hypotenuse, because that's fny and fn there. And so it's the same thing, but for the frictional force, it's a little different, just because the triangle's in a different place. I mean, if you have questions about this, feel free to try the office hours. But yeah, this is probably the hardest part of the problem, really, coming up with these trig functions. So you have to really make sure you understand how the angles work. Yeah. So with that, we have our three terms, and it turns out it's very nice for us. So we have the normal force multiplied by L times cosine theta minus a half times m times g times L cosine theta minus the frictional force times L times sine theta, and it's all equal to 0. So when we change everything to what their meanings are, so from our Newton's linear law, right, Newton's linear second law, we found that the normal force was mg, so we can just replace that with mg. Same thing for frictional force, mg times mu, right? It's just mu times n. So we have a lot of common stuff here. We have mg and L are basically all common, so we can cut all that out. Now we just have two trig functions left. So it's looking like it's going to be a hard problem, because if we try to do that just from cosine and sine theta, we might just get stuck doing arc sines and arc cosines forever. So one thing we can do is just divide cosine by everything. We'll divide everything by cosine separately, and then you'll end up with 1/2 minus 1/2 times tangent theta. If you just add that to the other side and you multiply by 2 on both sides, tangent theta equals 1. And so the only place where the tangent is the same is that theta equals, tangent of the angle is the same as that theta equals 45. And so the minimum angle is going to be 45 that they fall at.